So yeah, finally let's start with my talk. So I want to talk about the expressional power of hard attention transformers, especially on data sequences. This was a joint work with Pascal Bergstresser, Anthony Lin, and Georg Zetscher. And yeah, our paper got recently accepted to Europe's. So uh, okay, so yeah, I think most of you already know parts of this slide. So transformers are introduced in this paper from group from Google, which got a very incredible number of citations. I don't know whether this is a true number. Uh, it's very strange. And yeah, it's a basic model in machine learning using today's large language models. And it has some applications in natural language processing, computer vision, language recognition, time series analysis, and so on and so on. However, yeah, this artificial intelligence is often not so intelligent. So, for example, if you ask ChatGPT to count the number of A's in a string, um, and especially to decide whether it's even or odd, yeah, then yeah, then it gives you some random number. In this case, it says 19 A's, which is odd, but actually, yeah, this string can contain 22 A's, which is an even number. And yeah, to be honest, this is a very complicated example. You can also do this with easier examples. For example, just ask ChatGPT to count the number of R's in the word arbitrary. It says two. Uh, yeah. So there are some questions. So what can be expressed in transformers or activity or whatever? So for example, parity is expressible with transformers, but yeah, we cannot train this to parity. So that's the reason why ChatGPT is not able to decide this problem. Um, and yeah, another question is how can we verify incorrectness or correctness of transformers? And yeah, and so on and so on. These are typical questions for verification. Uh, there's already much research already done on transformers with words as input, but transformers that take more complex data are not much covered in research until now. And this is what we want to change now. And especially we want to tackle the first question here for these transformers. Okay, so what's a unique hard attention transformer or U-hat? So it takes an input sequence, which is some word or some finite alphabet, plus some end of sequence symbol, end. And yeah, the sequence has an arbitrary length, n. And then we apply some arbitrary function, the word embedding, just to translate the letters from our input into vectors of real numbers. And then, yeah, we also apply or we are allowed to apply some positional encoding, which is an arbitrary function, which takes the position and the length of our input and output some vector. And yeah, it just appends this positional encoding uh, to our vector in this sequence here. Uh, especially, uh, we say there's no positional encoding if we just say yeah, everything is zero. Then finally we can apply several layers. There are two kinds of layers. First kind is the attention layer, which takes a sequence of vectors, of course, and it constructs a matrix for each pair of elements in the sequence. And in a cell ij, we just put the attention score, which is some measure of the relation between in this case these two elements. And this attention score is derived by uh, applying two affine transformations to each of these elements and then just take the scalar product. Then uh, yeah, for each element or for each row, we pick this element which relates the most to this element. So which has the maximum attention score, and this is the attention vector AI. And in the case of a tie, we always take the leftmost vector with this maximum. In case we don't have a positional encoding, then we allow a special mechanism called path masking, where we just ignore everything on this lower triangle in our matrix. And yeah, one special case, we do not mask this Vn because we have to choose one of these elements, of course. Well, now let these be attention vectors, and then we obtain some new sequence of elements from the previous element in this position and its corresponding attention vector by applying some affine transformation. Well, that's the attention layer. Then we also have a value layer, which just applies to each element in our sequence this value function to one specified component. And this means, we just replace all negative values by 0. Okay, after applying k layers, we get some output sequence, and then we want to check whether we accept the sequence by taking a weighted sum of the first element in this sequence, and these weights are just some given vector. The output is 0 or 1. Well, this is a U-hat on words. Now we wanted to talk about oops, wrong direction. Data sequences. So now our inputs are vectors, sequences of vectors, especially we have rational vectors, and our end of sequence symbol is just a 0 vector. And since we already have vectors, we don't have to embed this into the real numbers, and so we can just remove this first step of word embedding, and this is a unique hard attention transformer on data sequences. Well, let's talk about our first result, which concerns circuit complexity. What you already know is every word language accepted by a U-hat with positional encoding is an AC0. AC0 means this is the class of all languages accepted by a family of circles of constant depth, polynomial size, and we only use Boolean gates with unbounded number of inputs. Especially this is a proper subclass. So Marcello et al. Could show that there is some language which is an AC0 but cannot be accepted by a U-hat. And what we can show or what we could show, is that every data language accepted by UHAT, uh, with positional encoding, of course, is in TC0. So it's some uh, superclass of AC0, which means, yeah, it's AC0. Plus, we are allowed to use maturity gates. So maturity gates is just, it takes a number of inputs and it outputs one if the majority of the inputs is one. Otherwise, it outputs zero. And so this is one of our results. And the other result is there is a UHAT, even without positional encoding, which accepts a data language that is not in AC0. And well, to be fair, uh, I think that the class of data languages accepted by UHATs is just incomparable to AC0 because I think that this language here is also could also be not accepted by UHAT with on data languages. So yeah, we are on TC0, but incomparable to AC0. Well, uh, how can we show this? So first, why are we in TC0? So first, recall one, yeah, famous result. Multiplication of two numbers can be realized in TC0, but not in AC0. Um, well, but this is not a problem in the word case, because in the word case, if we don't have to multiply arbitrary numbers. Uh, if we have the input of length n, then our UHAT sees only a finite number of real numbers during its computation on any input on this of this length n. And so we can just compute symbolically using some fixed table, and that's the reason we stay in AC0. The problem is this is impossible in the data case, because for any sequence of length n, we can see infinitely many real numbers during the computation of our UHAT. And that's a problem which we had to solve. And what we could show is if our input has a bit length L, then we could approximate each of the real numbers in our UHAT by rational ones of polynomial bit length. And after we approximated all of these numbers, then translation into TC0 is easy because we just have a bounded number of additions and multiplications, which is realizable in TC0.
Chris, quick question.
Yes.
How is the input specified for data words on circuits?
Yeah, so our inputs are vectors on rational numbers. So yeah, just encode each rational number by two integers with some symbol in between. And
Well, there's a symbol in between. So the length of one position may be different than the length of another position.
can you say it again?
When you encode one rational number from the input, the length of that encoding from the point of view of the circuit depends on the number.
Yes.
Which means that each input is not same size.
Yes, that's right. So yeah, we have to be really careful here. But yeah, if our input is has length L, so the complete input has length L, then we can approximate this with rational numbers of this polynomial in L. Okay. Okay. So now we are in TC0. Next question is why aren't we in AC0? So let's consider this problem from bus. Given three integers, a, b, c, and we ask is a times b greater than 0? And this problem is in TC0. It's even complete in TC0 under AC0 reductions, which means it's not in AC0. Yeah, we can also translate this problem as follows. So instead of asking whether a times b is greater 0, we can also say, yeah, this is the same as a is greater than c divided by b. So what we have here is a comparison between two rational numbers now. And so a times b greater 0, greater c for three integers reduces to in comparison of two rationals. And the latter problem is accepted by a U-hat with 0 layers, which only has this acceptance vector 1 and -1. And yeah, this means we just compute r minus s and check whether this is greater than 0 or not. That's all we have to do. Okay. Let's talk about our next result, which are regular languages. Well, it's not clear what is a regular language on data languages, data. So yeah, what we do is the following. We just start with an NFA, but yeah, we cannot just replace the letters on our transitions by a vector, because then we still have just some boring language, because then we still have a word language, which is boring. And what we do instead is we replace each edge label by a set, a subset of the rational vectors. And especially those sets which have a decidable membership problem, and also for verification purposes, we also require that the emptiness problem should be decidable. For example, we have this automaton. So now we can say, we have a vector which satisfies the formula that's x1 plus x2 equals x3, or x1 is greater than 0, or something like this. Let's see how this works. So we start in the initial state, q0, and then you read some vector, in this case 1, 2, 3. And then we have, in this case, two transitions which are enabled. This is one transition is this one, because x1 is greater than 0. And then we also have this transition, because 1 plus 2 equals 3, of course. So this is also enabled. And we don't deterministically choose this transition now. And then we read the next vector, 0.1, 0, 0. 0.1 is greater than 0, so we can, for example, just take this transition and go to Q4, and finally we can check whether x3 is equals to 42. And so we arrive in final state, Q5 in this case, and this means this sequence here is accepted by this so-called symbolic automaton. And the set of all languages accepted by a symbolic automaton is set of all sequences of vectors which have run from the initial state to one of these final states. Okay. the regular data languages now.
One small clarification, if I can. What's the labels on these transitions? What are we allowed in terms of arithmetic?
Anything with which has decidable membership and decidable emptiness problem. That's all.
Okay.
So in general, so typically we just use arithmetic constraints like what we can see here,
Okay, cool. Thank you.
but probably there's also more complex constraints. Um, what we know is, uh, yeah, these languages accepted by such symbolic automata uh, share many properties with the classical regular languages. For example, closure properties, especially closure under Boolean operations. We can also determinize these non-deterministic automata. And yeah, we can also decide the emptiness problem, which is important for verification problems. Well, so what we know from Nguyen et al. Yeah, actually, all of these three authors are here in the audience. Oh no. Yeah, everyone is here. Okay. Uh, and we know from this paper that every word language that is accepted by a U-head without positional coding but with masking uh, is star-free and hence regular. Especially these U-heads accept exactly the star-free languages. Uh, we can show some negative result here. We consider the following data language called double, which is just a sequence of rational numbers. And yeah, this means for each element in the sequence, the right neighbor is at least or is greater than the double value of this element. And yeah, for example, we have 0, 1, 3, 7, 15 is a double, or -20, -9, -4, -1. And this is some counterexamples, 0, 1, 3, 5, 20. This is not in double. And yeah, this data language is not regular, but it is accepted by a U-head without positional encoding and with past masking. So we are in the same situation, just that we use data languages now, uh, and we accept something non-regular. Yeah, why is it not regular? Yeah, this is some typical pumping arguments. So to decide whether uh, yeah, the next element is valid, we have to store this value somewhere in our state, and we always have to double this, and we can do this only finitely many times. And so yeah, it's impossible to do this with symbolic automata. Um, Especially, there are also other kinds of generalizations of NFA. There are register automata, which also have some finite number of registers. And this language is also not regular in this sense. Uh, but this is it is accepted by U-head, which you can see on the next slide. So yeah, we just proved this with an example. Let's consider the sequence 0, 1, 3, 5, 20 plus 0 at the end. So end marker. There's just one problem because we cannot distinguish these two zeros. And what we can do now is we just add some indicator. So some lightweight positional encoding which says, yeah, this is the end and anything else is not the end. And now we can do the following. uh, we do some attention layer with the following semantics. We check for each pair I and j that two times uh, the ith value is smaller than the jth value, at least if I is smaller than j, and also if j is smaller than n. Um, Especially if j equals n, then we always want to have this value 0. And we realize this with the following tension score, which is just the jth value minus two times the ith value. And to obtain this 0 here, we multiply this with this indicator, which says, yeah, we are on the last position or not. Because, yeah, then we have 0 in this case if j equals n. Yes, here's 0, here's a 0, so this value is 0. And otherwise, this is just 1. So we obtain this matrix. And now we choose the last element if all of these elements before us negative. So if they satisfy this inequality. And yeah, unfortunately, here we have a 1, which means, yeah, we uh, yeah, which means 2 times 3 is greater than 5 in this case. Okay, and well, now we have our attention vectors, and from these attention vectors, we can just take this positional indicator. And this results in the split vector 0, 0, 1, 0, 0. And finally, we do some second layer, where we just check, yeah, whether all these bits are 0. And how can we do this? Yeah, we just check for each position that vi equals vj equals 0. And how can we do this? Yeah, we just state that the tension score is vi plus vj. And yeah, we take the maximum, so we take these attention values in this case. I don't want to call them vectors anymore. And what we do is just now we compute 1 minus the sum of, or actually just this attention score. And especially you obtain here a 0, and we test whether 0 times 1 is greater than 0, but no, this is 0. So yeah, the output's no in this case. So we don't accept that this sequence. And I'm pretty sure that for any sequence of numbers, this will give the right result, but yeah, who knows whether I'm really right. Okay. Yeah, let's talk about our third result, which regards logic. Yeah, so let's start with ATL, so linear temporal logic. This has the following syntax. You are allowed so we can use any symbol A from our alphabet, and the formula A is satisfied at position I in a word if, yeah, this word is labeled with A on this position. Then we have true, we have Boolean connectives. We have the next operator, x phi, and x phi holds on position I in a word W if it has some right neighbor. And on this right neighbor, phi holds. And we also have an until operator, and phi until psi holds in position I. If there is some element to the right of I, which satisfies psi, and everything in between satisfies phi. And yeah, in particular, this element satisfying psi could also be I in this case. Um, yeah, we also have some operations, finally or eventually, which means f phi holds on position I if there's some element to the right which satisfies phi, and globally phi, which is satisfied on position I if all positions to the right satisfy this formula phi. Okay, yeah, that's linear temporal logic. Let's consider an example. Yeah, first, so yeah, we just have some arbitrary formula and some arbitrary word. I don't know whether that's it's very it is some very interesting language. I don't know. Uh, yeah, so everything which is labeled with A satisfies this formula, of course. Similarly, these two positions are labeled with B, so they satisfy the formula B. Then these two positions satisfy the formula XB because, yeah, the position to the right is labeled with B. And then, yeah, all these positions which are labeled in violet, or purple, satisfy this until formula. Now, yeah, just make it a bit easier to overview. So just remove the subformulas. Then we label or we mark everything which is labeled with C. Then everything which says finally C. So everything which has some successor which is labeled with C. So this is actually everything. And accordingly, everything is also labeled with G in this case. So again, make it a bit easier to overview. And then, yeah, we just take the intersection of these two languages or of these two formulas, and these are these positions which are labeled in red. And a word is accepted or is described by a formula phi, yeah, if it holds in the first position of this word. And in particular, in this case, the first position is marked in red. So this is accepted by, or is described by this formula. And by Kamp, we know that the class of all word languages defined by LTL are exactly the stuff-free languages, aperiodic languages, counter-free languages, and also first-order definable languages. And this is also the class of all languages accepted by UHAT with masking, but without positional encoding, according to Engluin, Jiang, and Yang. Okay, now let's extend LTL with monetic predicates. Yeah, this is still LTL, but we have some new kind of atom. And this is some positional predicate. So we have some family of predicates, theta n, depending on the length of the input. And yeah, we satisfy some this formula theta at position I in a word W if yeah, position I is true in theta for the length of W. for example, uh, that our alphabet contain A and B, and theta n uh, on position I is true if n is even and I equals n half. And then we consider this formula here and this one word. And yeah, this word has length 8, so it's even. And uh, yeah, the only position which satisfies theta is in this case position 4, which is 8 divided by 2. And yeah, then these are all positions satisfying finally theta. And yeah, then the second formula just says all formulas or all positions satisfying this finally theta are labeled with A. All other positions are labeled with B. And this means the language described by this formula is the language of all words of the form A to the n, B to the n, where n is a natural number, which is not regular. And from Barcello et al., we know that the class of word languages defined by LTL-MON are accepted by U-hat with positional encoding in this case. And Encloin et al. Specified this a bit more exactly. They said, yeah, the class of word languages defined by LTL-MON is exactly the class of all languages accepted by U-hat that have positional encodings with a finite image. Okay. And in the data case, we have to extend this again. And this is the logic LTLTL or locally testable linear temporal logic. And here, yeah, it actually doesn't make sense to talk about single letters anymore. So what we do instead, we do arithmetic constraints. These are these atoms here. And in the sequence V1 to Vn, at position I, such a arithmetic constraint is satisfied if and only if we have at least k neighbors to the right, and if we append all the right neighbors, or the k right neighbors to vi, we take yeah just a weighted sum and compare this to this number b in this case, which is some given constant. Well, this is ATLTL, and let's consider this example phi, which says globally, whenever we are not on the last position, then minus 2 times this position plus the right neighbor is greater than 0. Or in other words, the right neighbor is greater than 2 times this actual position. So let's consider this arithmetic constraint. So first, here we compute minus 2 times 0 plus 1 is 1. So it's satisfied at this position. Then minus 2 plus 3 is also 1. So it's satisfied. Then minus 2 times 3 plus 5 is minus 1. So this is not satisfied at this time. And then, yeah, here we don't have a right neighbor, so this is not satisfied in the last position. And in particular, we can see, yeah, the language described by this formula is the language double. We have introduced some slides ago. Okay. Any questions so far? Okay. Let's consider some more examples. Um, Here we have some example which is related to the Skolem problem. So we consider linear recurrence sequences. So we have a rational matrix A and some rational vector Y. And for some vector X, we consider the following sequence, which consists of X, then A times X, A squared X, until A to the power of N times X, where N is minimal, such that the weighted sum of the elements in A to the N X is zero with the weights from Y. And this language can be described by the following formula. So as long as we are not in the last position, then the weighted sum of the elements or of the components in X1 is not zero. And A times X1 equals X2. And yeah, all of these equalities or inequalities can be uh, expressed using our arithmetic constraints we defined in LTLTL. And yeah, if we are in the last position, then yeah, the weighted sum of xi equals one, equals zero in this case. Okay, we have a third example, um, which considers the 7-day simple moving average. So in this case, we check for some uptrend in the time series, but it's not necessarily, yeah, it doesn't mean we consider some monotonically increasing function. So we can also have some dip in such a time series, but still an uptrend. And especially, so what we mean with this uptrend is the following. We accept a sequence of rationals if and only if at each time point the value is above the average of the week before, or the week ending at time t. And we can generate this with the following formula. As long as we have at least 6 right neighbors, then 7 times the last of these 6 right neighbors is greater than the sum of all these elements in our sequence. And this is exactly, yeah, what we said here, that the value is above the average of 1 week. Okay. Any question? No. Okay. Then, yeah. Now let's take some arbitrary formula from ATLTL. And what we can prove is that the data language described by phi is accepted by a U-hat with positional encoding. And this is what we wanted to prove now. We've still got some time. To prove this, we need some lemma, which we don't want to prove here. Well, so that there's some U-hat layer, which uses positional encoding, such that on every input, we always take for position I, the attention vector, which is just the right neighbor uh, of this element. And yeah, we just use this scheme to recognize this U-hat layer. We will use this a few times later in our proof. Then there's also some U-hat layer, which also uses positional encoding, such that on every uh, sequence V1 to Vn, with the property that there are some component L, such that the values are Boolean values at this component L. And we always pick the attention vector, uh, which has that no, we always take the attention vector where the L component of this value is zero, and it's always at the minimal one. So that this is used for yeah, for this until formulas in the end. And yeah, we use this scheme here. So especially, yeah, if you consider this example, yeah, then if we start with one, then the first zero is this position. So this will be our attention vector. This also holds for this position, this position. The next position for the first zero is the zero itself, and so on. Okay. And finally, there's a whole U-head in this case, not just a layer, uh, which also uses positional encoding, such that on every input V1 to Vn, we output the following. We just replace the elf component of our input, and we replace this by some indicator function, which indicates, yeah, that this value was positive or not. So we just compute, yeah, this indicator function. That's the fact we want to do. And now let's prove our result. So let phi be some LT-LTL formula, and we will construct some U-hat T phi m with positional encoding, such that an input V1 to Vn, where everything is m vectors, and we output m plus 1 vectors as follows. Well, we just keep our input and add some new component where we have where we say, yeah, formula phi is satisfied on this position or not. And we prove this by induction on phi. So the simplest case to prove is, yeah, uh, this positional formula theta, and we just do this with positional encoding. So we just set the positional encoding at position I to theta n of I, where n is the length of the input, and the last one is always zero. That's all we have to do in this case. For an arithmetic constraint, what we do is we first gather the k right neighbors of each element and just append them to one big vector. And we do this with this U-hat layer from the this lemma 2 slides before, which we apply k times. And in the last of these k layers, we output the following value, which is just, yeah, the weighted sum of these elements minus b. And yeah, in the end, we just apply this U-hat that computes the indicator function for xi. That's all we have to do in this case. Okay. Conjunction. So assume we already have U-hats for psi and chi. And what you do is we just concatenate these two U-hats, and then we compute the output of the U-hat for psi plus the output of U-hat for chi minus 1. And again, we just apply the U-hat that computes the indicator function. Okay? Negation? Yeah, this is, to be honest, really easy. So we take the U-hat for psi, and we just compute some new U-hat, which has some additional layer, which computes 1 minus the output of the original U-hat. That's all we have to do. Well, now consider the case next psi. So assume we have a U-hat for psi. And what we do is we just add a new layer to this U-hat, uh, which just yeah takes the right neighbor as attention vector, and then we just copy the output of this next position, yeah, to our new position. So we just use this U-hat layer uh, as mentioned before. And for the until formula, I already announced that we use this one special kind of U-hat layer. So um, to solve this formula psi u chi, uh, we assume we have a U-hat for the formula psi and non-chi in this case. And what we do now is we extend this U-hat by this one layer, which selects always the next position with value 0. This was this one with this scheme. And finally, we just return the value of chi at this position. And this is hopefully the output of psi u chi. Okay? Yeah, this is the end of our proof. Yeah, okay. To finally come to an end, what we did is we compared U-hats with circuit complexity classes. So you already know that U-hats on words are a proper subclass of AC0, but U-hats on data are subclass of TC0, but not of AC0, even if we don't use positional encoding. If you compare U-hats with regular languages, then we know U-hats on words, except exactly the Starfree languages. Okay, only in the case we have no positional encoding but masking. But in the same situation, we can show U-hats on data except non-regular languages. And finally, we compared U-hats with logic. So derived from this regularity result, we know that U-hats on words without positional encoding, except exactly the languages described by LTL. And in general, U-hats on words uh, except languages described by LTL-mon. And in our situation with U-hats on data, we extended this to LTLTL. Well, very complicated. Okay, thank you very much.